My name is Pax Hamar. I'm the Associate Director of Graduate Programs at the Stanford Center for Professional Development. And I'm here with Marco Pavone, Jeanette Volk, and Dorsa Sadiq, who will be leading a 2-course sequence in robotic autonomy that they just recently redesigned and redeveloped. And so we're here to find out about their research, robotics, and their course. Great. We'll start off with just each of you introducing yourself. So Marco, could you introduce yourself touching on your research?
Sure. I'm a faculty in the Department of Aeronautics and Astronautics, where I direct the Autonomous Systems Laboratory, and I'm co-director for the Center for Automotive Research at Stanford, and I'm also affiliated with the Human-Centered AI Institute. My work is on decision-making and AI algorithms for robot autonomy, with application to self-driving cars and autonomous aerospace vehicles.
Perfect. Jeanette?
Thank you. So my name is Jeanette Volk. I'm assistant professor at the Computer Science Department for Robotics, and I'm directing the Interactive Perception and Robot Learning Lab in the CS department. I'm also affiliated with the Human-Centered AI Institute, as all three of us. And my research is at the intersection of robotics, machine learning, and computer vision, and all the algorithms I've been developing in the course of my years of research are applied to the problem of vision-based or sensor-based robotic manipulation and grasping. Thank you.
Sure. So I'm Dorsa Sadiq. I'm an assistant professor in the Computer Science and Electrical Engineering department here at Stanford. I'm also the co-director of the AI Safety Center, and I'm also affiliated with High Human-Centered AI. So my research is at the intersection of robotics and human-robot interaction, thinking about design of algorithms for autonomous systems that safely and reliably can interact with people.
Perfect. And Dorsa, as a follow-up, I know you have sort of an interesting path to the research that you're currently doing. Can you tell us a little bit about that?
Sure, of course. So at the beginning of my PhD, when I started thinking about what to do, I was looking at robotics and formal methods. So I really wanted to work at the intersection of these two fields, where formal methods is this field where you're looking at giving correctness guarantees for autonomous systems. And the goal of my PhD thesis was to give guarantees for autonomous cars. The autonomous cars were becoming a thing at that time, and I really wanted to be able to give provably correct guarantees for these systems. And soon I realized one of the biggest problems with autonomous cars when you're trying to give guarantees about them is just dealing with humans. There are all these human-driven cars around us. And if we don't have good models of them, or if we have made-up models of them, then we can give some sort of guarantees. But it's important what sort of models we are picking and how we are deciding, like, what are the humans around us are doing. So I do think this area of human-robot interaction is really interesting, and that's how I got into it and how I started thinking about interaction and the fact that autonomous systems, robots, are coming into our everyday lives, and we need to think about that interaction and the fact that there are humans around us, and we should model them in a way that's useful for our autonomous systems and robots.
Fantastic. So you touched on there one of the big challenges for roboticists today. What are some of the other challenges for robotics?
Yeah, so I think it's a very good time for robotics. I think there are a lot of interesting opportunities and interesting challenges in robotics. So one of the biggest ones is, I think, dealing with humans and dealing with uncertain environments. I think in addition to that, we have a few other challenges, things like generalizability and how we can think about like combining model-based and data-driven techniques and how we should go about that for solving really difficult robotics problems. And then going back to uncertainty, I think another difficult problem is thinking about giving guarantees and safety and how we can plan like under uncertainty and how we can give probably correct guarantees and going back to the safety problem, how can we give guarantees for our autonomous systems?
Marco, I know you also work a lot on decision-making in uncertain environments. Can you elaborate on that challenge?
Yes, absolutely. Robot autonomy really entails designing robotic systems that need to operate in situations that cannot be foreseen at the design stage. And those situations require reasoning. So the challenge is how do we provide assurances and guarantees for robots that need to respond to situations that cannot be foreseen at the design stage. So a good portion of my work is devoted to techniques that allow robots to generalize their behaviors to situations that cannot be anticipated at the design stage, and in a way so that we can have trust in and confidence in what the robot does.
And Jeanette, your work works you also focus both on sort of this problem of generalizability as well as some of the challenges that Dorsa touched on the models that we use. Could you develop that?
Right, yeah. So maybe also just to expand on what Marco just said, the problem of having a robot act in an uncertain environment is also something that I'm very interested in. It's a very hard problem, and it's typically engineered away in environments like car manufacturing factories, for example, where the environment is designed in such a way that a robot doesn't have to deal with uncertainty at all and can just execute pre-programmed motions. But if we aim for having the robot actually help us in our house, at home with annoying tasks that nobody wants to do, or in dangerous environments that we don't want people to actually be in, a robot will experience all these unstructured environments. And it only has sensors that that basically give it access to partial information only. And still, it needs to be able to make safe decisions on how to act in this environment, and also robust ones. And even if it makes a failure, it should be able to recover from this failure and redo. And these are all challenges that we don't know really how to do today, and it's very exciting to work on those. Yeah.
So sort of building on what you said, or if Marco or Dorsa, if you want to chime in, but you've talked about in the past also the challenges of collecting data, that it's very expensive and can be dangerous to collect data with robots. Can you build on that, or if anybody wants to speak to that?
Right. So I can maybe start talking about this. So there is a huge opportunity right now in robotics to actually use machine learning-based methods to enable robots to do tasks that were previously not possible, because maybe we cannot have good models, like, for example, in the human case, or also in terms of physics-based models of, for example, fluids or deformable objects. And learning-based methods allow us to maybe learn models instead of having to hand design those for these difficult physical processes, for example. But current machine learning approaches rely heavily on large amounts of data. And in other applications like computer vision or natural language processing, this kind of data is relatively easy to collect and to label. But in robotics, what it means to collect data is typically to have an actual physical machine interact with the environment in such a way that it doesn't destroy itself or is a danger to anyone around it, or breaks anything in the environment. And also it takes just longer for a robot to execute a motion rather than just looking at a picture and labeling it. And therefore, it's actually much bigger effort for a robot to collect that kind of data that is required for current machine learning techniques. So I think there's a huge opportunity in robotics to use machine learning, but it also poses a challenge to actually that is very specific to robotics, where it's hard to collect enough data for current algorithms.
And I think just to add on what Jeanette was talking about, I think another opportunity here is, like, we've seen all these advances of deep learning in natural language processing and vision, and one of the reasons is data. But another interesting thing is we've been using model-based approaches for robotics for many years, and these model-based techniques can provide really good priors, really good inductive biases, and actually help us improve a lot of deep learning type techniques that we have. So it actually helps us improve machine learning too, having this new problem that we have, in addition to having extra data. I think there's a lot of interesting directions that one can take, thinking about data-driven and model-based, and how we should combine them to solve some of these really difficult problems in robotics.
Yeah, and if you think about it, it's interesting how in the AI community, oftentimes people consider the abundance of data as a challenge. In robotics, we have a bit different challenge. It's the scarcity of data, which, as Dorsa and Jeanette were saying, opens up an opportunity in order to devise techniques that are really tailored to robotics and creatively combine model-based approaches with model-free approaches and carefully designed ways of collecting data and so on and so forth.
Fantastic. What are some of the other opportunities that you see for roboticists today, Marco?
In terms of research or in terms of applications?
Both.
In terms of research, so we talked about generalizability. We talked about how to interact with humans in a seamless way. I would like to reiterate the challenge that an opportunity that Jeanette mentioned, which is the one of interacting with the environment. Usually for robotic systems, as long as they do not touch something, you can still do it. But the moment they start touching, manipulating, affecting the environment, then it becomes a gray area with a lot of open questions. And then the aspect of safety. Safety is a difficult concept in the context of robotics. First of all, different applications demand different levels of safety. Of course, safety for self-driving cars is different than safety for a warehouse robot. And second of all, it's a concept that needs to be traded off with efficiency, meaning that as humans, we constantly make good judgment calls in how to properly trade safety with efficiency. It's relatively easy for a self-driving car to be safe, just as it moves. Or it's relatively easy for a self-driving car to be very efficient. It always go at maximum speed, but sometimes it might collide. The question is, how do you trade the two in such a way that you find the sweet spot? Now, finding techniques to achieve that trade is still very much an open challenge.
Dorsa, could you build on that? Because I know you've done research both on that sort of trade-off of efficiency and safety, as well as the interaction with humans, right? Because robots can start influencing humans as well.
Yeah, so I think the influencing humans is also another interesting aspect of it. And it goes back to like interacting with the environment too, right? Once we are touching the environment, we are changing the environment. Once we are interacting with the person, we are changing the person. We are influencing the person. And thinking about how our actions as an autonomous car or as a robot is going to influence humans and how are humans going to respond and how their models change is actually really interesting and challenging. And just to build up on what Marco was just talking about, so we have all these different challenges which are really interesting, and you're doing research on them, and it's exciting because you're teaching a class that's trying to like cover all these topics that are these new exciting topics in robotics. But I think there are a lot of interesting opportunities in industry too. So I think these are like academic, like from an academic perspective, these are challenges and problems that we can go about solving and learning about. But from an industry perspective, we've seen robotic systems like in factory floors, like mainly working in factory floors and doing awesome things. But we haven't really seen them like coming into our everyday lives yet, right? Like autonomous cars is kind of a step in that direction. But in general, I think there's a lot of interesting opportunities from an industrial perspective, from an application perspective, thinking about robots coming into our everyday like life. Thinking about helper robots or companion robots or robots helping in like hospitals or in homes, like especially with our like elderly population increasing, I think it's an interesting opportunity to look at. There are other applications like agriculture or like space, like as Marco works on, that we can think about how robots can help us and actually coming into our everyday lives in a more like tangible way.
Yeah, and that's a very good point. And in fact, one of the key motivations for us to develop this course series is to, in a way, democratize the tools behind the robot autonomy in hope that we can spur a new set of ideas from industry, new set of applications that, as of now, we are not even aware of.
I think that might be a good transition. I want to come back to some of the things we've talked about, but maybe to discuss the classes themselves. So, Jeanette, what is one of the things that you're most excited to teach in this course?
Right. So, as Dorsa already said, we are actually touching on 4 areas within the course, which is learning-based method for robotics, systems integration and verification and validation. We're looking at physical interaction for manipulation and grasping of mobile robots, and we're looking at interaction with humans. And on none of these topics is really taught yet, at least at Stanford, in this integrated way on an actual platform. And so first of all, I'm excited about this kind of cut through all of these areas, because typically in robotics, people are very focused and almost a bit siloed in their particular areas. So they are perception experts, control experts, motion planning experts, human-robot interaction experts, and they typically don't know the field of these other fields very well. But a robot is actual physical system in which all of these things have to come together. And if you put modules together that are developed in an isolated manner, they may not actually work that well together if you put them into a system just as is. So this course actually provides this opportunity to put all of these different kind of components of a system together and actually see what happens and what is required on a systems level as well. So that's something I'm very excited about, actually.
Please subscribe the channel for more videos.